This is Lab 3 Circuits for Physics 2212 by Camille Branch. The purpose of this lab is to predict the behavior of circuits containing resistors, measure the potential differences around a circuit, examine the behavior of resistors and capacitors over time, and calculate the RC value in a circuit. And then for this experiment, we'll assume that the resistance in the wires are negligible and the resistance in the ammeters and batteries are negligible. So for some fundamental principles, we have a couple of equations and theorems. We have a loop rule, which means the round-trip potential difference of a circuit in steady state is 0. The node rule, which means the current entering the circuit node is equal to the current leaving out of it. The potential difference of a capacitor is IR. The potential difference of a resistor is Q over C. And then the potential difference of an RC circuit and finding the RC values are equal to those equations listed. And then in the two figures, we see visual representations of the node rule and the loop rule. So for experiment 1, we have the system as the circuit and the surroundings as the earth. And for the procedure, we set up a circuit matching the diagram, measure the current, and then reverse the connection and measure it again. And then we set one of the ammeters to voltmeters and measure how many volts it is. Then we create a series circuit with those things mentioned, and then take note of the brightness while measuring the current at each node. And so for the data collected in that, the potential difference around the circuit, starting at the batteries and ending at the ammeters, we find that the change of potential difference is 0, and we expect this due to the nature of the loop rule. And then for experiment 2, we have our system as an RC circuit and the surroundings as earth. And so for that procedure, we charge a single capacitor using two 1.5 volt batteries and record the time it takes to do so. We then create a circuit that only consists of a light bulb and the charged capacitor. And then we record how long it takes for the light bulb to completely dim. And then that is the circuit and the figures here. And then the data collected, we found that the time to charge the capacitor was 12 seconds, and the time to discharge the capacitor was 20.61 seconds. And then what we observed was that as the capacitor discharged, the light bulb grew dim over time, and the capacitors serve almost like a rechargeable battery for the light bulb. And then some possible sources of error was that we could have had incorrect voltage readings, incorrect resistance readings, and calculations. The surroundings could have affected the circuit, and we could have had faulty materials. Okay, and then here is the what if question. What if you charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So with no resistors in the circuit, our model predicts that the capacitor will be extremely fast in ideal conditions because there's no resistance. However, because these aren't ideal conditions, you have resistance within the batteries and resistance within the wire, and also the effects of the surroundings. The real life value compared to the predicted value will be larger in time, which means it will be slower to it'll be slower. Thank you.